all the time. And that's, of course, very expensive, and it's just one of several hyperparameters you tune when you try to design these neural networks. So to get a sense for why something like a global Lipschitz constant of the function class may not be a good model of what's happening in the optimizer, let's take a look inside sort of the architecture of a neural network. And here I'm going to, for this talk, mainly focus on a relatively simple architecture just to get the point across. And the simplest one, of course, is a feed-forward multi-layer perceptron. So here, you have your input X, you have your output Y, you have these hidden states, and the hidden states are denoted H1 through H capital N. And the way that this function is parameterized is you have a sequence of functions, f sub n, which has each has its own parameters, theta sub n, and it takes as input the outputs of the previous layer, and it applies this function, and then it outputs the outputs of the next layer. And of course, the canonical example at this point is the ReLU in terms of the actual functional form, a linear transformation with a ReLU activation. And intuitively, what's happening here is that this compositional function that is a deep neural network is doing a sequence of transformations of the data from the original space through this. Each individual layer gives you a different representation, and eventually you get to a representation that's easy to classify in the last layer, which hopefully is linearly separable if you're doing classification. Okay, so this is sort of one way to think about sort of the structure of a neural network and to get some insights for why this might help us design a better optimizer. The first idea that we're going to talk about in this talk is per layer perturbation analysis. In other words, how does a single layer's function change under parameter perturbation? So if you look at a single layer from one layer to the next, then you have this parameterization. And we ask, okay, if we just perturb the parameters of that layer, how does that affect the overall function if we do a per layer perturbation analysis rather than a global perturbation analysis where we flatten all the layers' parameter vectors into a single flat vector? And benefits of this could be depth and width invariant learning rates if you can sort of do this type of analysis. The second idea, which I'll spend a little bit less time on, but will be in the second half of this presentation, is how do we actually control the dynamics of the hidden layers, right? If you think about the neural net as sort of doing this sort of as a dynamical system where the hidden layers are the states of the dynamics, then how do we actually control the sequence of hidden layer activations quickly and robustly to a low loss solution under some definition of low loss? And I'll give you one example of this in the second half of this presentation. More generally, the more fundamental question is how do we actually exploit the structure of neural networks to develop a more nuanced theory of optimizing neural networks? And in the first half, I'll present work in using the majorize-minimize framework and specializing it to architecture-aware perturbation bounds. And in the second half, I'll present work on using control-theoretic shaping of neural ODEs. Okay, so let's start with the first half. So warm up just so we're all on the same page. We're going to go back to first-year calculus and talk about the Taylor expansion. So you have your loss function, you have your theta, and you have a perturbation to theta, your weight vector, your parameters. And Taylor expansion is, basically writes things out in this form. And, if we look at the first two terms of the Taylor expansion, it's centered around the loss function at the parameter theta plus this linear approximation. And then you can write out this linear approximation as kind of like this tangent line to the point that you're at on the loss function. And the thing that you notice if you look at this figure is that this linear approximation will break down as the size of the perturbation increases, as you go further and further away from this reference point, which I've labeled as theta naught. And a lot of the perturbation analysis the goal is to understand the rate of this breakdown. And so the majorize-minimize framework is it's like this really basic framework that is the underlying principle of many optimization procedures such as gradient descent. And it works as follows, and it's very generic. It says, okay, I'm at this current point, theta naught. The first thing I do is build a majorization. What is a majorization? A majorization is an upper bound on the whole loss function, the whole objective, that lies tangent to the loss function at the point theta naught. That's what a majorization is. And then I minimize the majorization. I find the point that minimizes the majorization. That's my new iterate in my optimization iterations. The typical form of a majorization is to do some sort of Taylor approximation, where k is the order of the Taylor approximation, plus this upper bound of the rest. If you're doing things like gradient descent, k will equal 1 because we're doing a linear approximation. And then you need to upper bound the rest, and the sum of these two creates this majorization. So majorize-minimize framework can be specialized to produce many of the algorithms we use today. The first example, if you use a first-order Taylor approximation plus an isotropic quadratic upper bound on the rest, you get gradient descent. If you use some other form of Bregman divergence, you get things that look like mirror descent. If you use a second-order Taylor approximation, where the capital H in there is the Hessian, the second derivative, and then you do this cubic regularization on the end as a majorization, you get cubic regularized Newton. As a quick aside, you can think about the duality between majorization and truss regions. So for example, this is the majorization for gradient descent. People like it because this particular majorization has a closed form solution, which is the formula you see implemented for gradient descent. It's the closed form solution to this majorization. It implies the gradient descent update rule. And it's analogous to this dual formulation where we say we want to minimize this linear approximation to my objective function subject to the size of my perturbation to theta not being greater than, in this case, some capital C. This is just a dual formulation of the majorization. And people often refer to this as a truss region. So sometimes I refer to majorization and truss regions kind of interchangeably in terms of conveying the intuition with this understanding. So I'm not going to be very precise sometimes, just so you're all clear on this. And again, the theoretical guidance from classic optimization theory is based on this perturbation sensitivity, such as using a global Lipschitz constant. So if we, and one of the things about a lot of the classic theory is that if they try to, they by and large, they kind of flatten the weight vector of each layer of weights into this single flat weight vector, and they do this global perturbation analysis of the entire, all the weights flattened at the same time. And just for lack of a better term, I'm going to call this an architecture-naive majorization, where architecture is the architecture of the deep neural network. In some places in this optimization landscape, you can use a bigger step size, which corresponds to a smaller lambda here, which allows for this shallower majorization, which means I can take a bigger step away from this current place I am. In other places, I need to use a smaller step size, which means a steeper majorization, which means I'm going to likely make less progress because the majorization is going to lead to an optimal solution that's closer to the original iterate. And deep neural networks indeed have this very complicated optimization landscape. And so using a single isotropic majorization everywhere can be very inefficient as a way of capturing these efficient local models for this optimization technique, which is what gradient descent does. So having said all that as motivation, the key technical question that we ask, and this is work by my former PhD student Jeremy Bernstein, along with former undergrad Kevin Huang, who's now a PhD student at the University of Washington, is how do we define a majorization that exploits the neural network structure? And the first key idea that we're going to use to start to develop this technique is this per layer perturbation analysis. In other words, perturb an entire layer, but only a single layer's parameters, and evaluate the perturbation of the output of the neural network. So we vary only the nth layer for some layer n. And a thought experiment you might ask at this point is, well, what is the Lipschitz constant over the entire function f in response to just perturbing the weights of layer n? The answer, as some of you may have guessed, is that it depends on the value of the parameters of the other layers. If the other parameters are large, the perturbation is going to be larger. If the other parameters in the other layers are small, the perturbations on the function output will be smaller. So using that kind of insight, we can start to derive architecture-aware perturbation bounds that can be fitted within the majorize-minimize framework. So for squared loss, you can do the first order Taylor, upper bound of the rest, that this part is just same as before, but then you can start to expand it, and then you get something like the overall perturbation sensitivity as one of the terms in the upper bound, which is the sensitivity of the function itself, and then a breakdown of the linear approximation. And then you can start to upper bound these terms, And the thing I want you to notice, I won't like deconstruct every term in here. If you're interested, you can read that archive link, which is actually Jeremy Bernstein's PhD thesis. You get this thing that Jeremy calls deep relative trust, which is that you start to design this majorization or analogously a trust region that depends on the relative magnitudes of the perturbation with respect to the size of the weights in each layer. And this intuitively makes sense because, as I mentioned before, how the overall function output gets perturbed depends on the norm, the sizes of the weights in all the other layers. So that it depends on whether you're increasing the norms by 10%, 20%. And that's how you should think about sort of this kind of analysis. Okay, so the overall framework, looks something like, and this is very generic at this point. You derive a majorization of the error at your current iterate. And then we plug in one of our architecture-aware perturbation bounds rather than this isotropic quadratic. And then we minimize this majorization to get our next iterate, and that's our optimization algorithm. There's a few different desiderata and caveats I want to highlight. The bound that I'm showing here is only for deep linear networks. The formula looks similar, but has a few more lower order terms. And so therefore it's more complicated with nonlinearity, so I'm not showing it for brevity. But even this bound for deep linear networks, to our knowledge at the time that we presented this work, was the first ever analysis for deep linear networks for more than 2 layers, arbitrary number of layers. Another issue with this using this majorization is it doesn't have a closed form solution. So unlike gradient descent, where you don't actually have to solve this inner minimization problem because it has a closed form solution, this one does not. So solving for the optimal step in the optimization of each inner loop is itself an optimization problem. But maybe one thing to think of at this point is, we believe, and I'll show you empirical results in a little bit, that it's very important to be able to actually have a really good model of this local optimization problem within the majorize-minimize framework. So maybe it's good to sort of give up on having sort of the best iterate under this inaccurate model, which is what gradient descent does, and get a suboptimal iterate, but using a more accurate model of the local optimization problem. And under that philosophy, Jeremy and Kevin proved the first result in a series of results. And that is, okay, what if we enforce the relative update of each layer to be the same? So now we're constraining the majorization. We're constraining this majorization further. We're saying we only consider solutions to this majorization where the relative updates of each layer is the same. So for example, each layer's update is only updated by 10% or 5% relative to the magnitude of the weights of that layer. So what this means is you get a suboptimal but closed form update rule. But it's suboptimal with respect to a more nuanced and accurate, if you will, majorization of the optimization problem. And so let me walk you through what this optimizer does. So as before, theta sub n is the current iterate of the nth layer of layer n. Capital N is the total depth. The green term is the dimensionality of the 2 adjacent hidden layers before and after. We normalize the gradient, so it's just a unit vector. And then we do per layer scaling. So what this means is that you tune this global step size eta once, and then you could adapt this step size adaptively to have an adapted step size at each layer. In other words, you can tune this learning rate once for a really small, shallow network, thin network, and transfer this eta to much deeper and wider networks using this first result. For those of you who are familiar with mu parameterization by Greg Yang, this is very closely related to that earlier work. I believe Greg Yang's work at that time only applied to width transfer, not width and depth transfer simultaneously. And the proof technique to derive this is arguably much simpler for this result than the earlier results. So you can think of this as a generalization. So here are some empirical analyses. So here we're looking at, you're looking at 4 plots. They are neural networks of different depth. You are looking at, the colors code gives you different width from 64 to 8,192. And the x-axis of the plot is the learning rate, and the y-axis is loss. So lower is better on the y-axis. And the thing I want you to notice is that across depth and across width, the same global learning rate, which then gets adapted with the adaptation law that I showed earlier, is more or less optimal or near optimal for across all of these network architectures. And this applies, this of course is consistent as you train for longer and longer epochs. So this is just the first result. The latest result, which is by Jeremy and a PhD student from Oxford named Chris Mingard, is called automatic gradient descent. And in automatic gradient descent, it's built on the same idea, and it makes two further contributions. First, we have a special way of doing initialization, which implies that the norm of each layer's weights has this property, which, of course, if you remember, appeared already in the update rule. And then we have an automatic way of setting the learning rate here. And this overall preserves some certain properties of these weight matrices, which allows you to be hyperparameter free. So you don't even need to set the learning rate manually. It's set automatically once you've controlled for these factors. And you could look at some of our recent results, which we got working on ResNets, on CFAR10, and I believe ImageNet more recently, which I'll show you shortly. And the solid line is training performance, and the dotted line is test performance. Let's look at the dotted lines. And the x-axis is learning rate. Our algorithm, automatic gradient descent, has no learning rate. So you just run it once. And the thing I want you to observe is that it matches the performance of Atom and SGD that is tuned. And this also appears when you try it on ResNet 50 on ImageNet. And we're currently thinking about ways of scaling this up to other architectures such as transformers.
Something about wall clock time?
It's slightly faster than Atom per iterate.
What about SGD?
Slightly slower than SGD, I believe, per iterate. Yeah. And there's also memory, because Atom actually has to keep track of quite a bit of memory in its iterate computation, so it's also less memory than Atom. Here's another case study. We just thought, what if we just tried to train a really, really deep neural network that's normally really hard to train? So this is not a neural network you might want to ever use in practice right now, because this neural network is fully connected with no skip connections. So the deep networks usually have residual skip connections, and no batch norm, no normalization layers. So this neural network is bare bones, no bells and whistles. The gradient, it's really hard to propagate gradients through this neural network. But just as a thought experiment, if we wanted to train a neural network that's just hard to train. And so what you see here is that as the depth of this neural network gets larger, Atom and SGD just completely fail to learn anything on this network, whereas our approach is still able to learn a non-trivial model, just as an interesting case study. Of course, there are different ways to design these types of optimizers that are architecture aware. What I showed, so if the matrix on the right is like the weight matrix of a layer, what I've presented to you most today is a per layer perturbation analysis, where you look at the entire matrix of a layer. You can do per neuron perturbation analysis, where you just look at a row of this matrix. That's one neuron. You could even do per synapse if you wanted to. So there are different ways to be architecture aware, and per layer perturbation analysis is only one of several ways. And there may be others that we haven't thought of yet. And by we I mean Jeremy, has sort of led this foray into all of these different ideas. So if you're interested, I'm happy to share these references.
I have a question.
Yeah.
So when you said you only did it for linear models, does it mean you didn't have your positive part of the function, or did you have it?
You're talking about the bound I showed?
Yes.
The bound I showed is a clean bound for presentation purposes for linear models.
So by linear mean it's really...
There are no ReLUs. There are no nonlinear.
Linear,
Yeah, that's right. So this particular bound that I'm showing for presentation purposes is only for deep linear networks, for arbitrary depth.
So a related question is, once you put this positive part, or whatever you call it,
Yeah, it creates lower order terms. So
it's not differentiable, right?
It's differentiable almost everywhere.
I see. So in practice, it's not a problem.
No, it's differentiable almost. It's non-differentiable on a set of measure 0. No. Yes.
Do you have rank bottlenecks in these deep neural networks?
No, no. These are no. These are just fully. This particular. Okay, if you do like convolutions and other things, it creates a bunch of lower order terms. The bound gets messy. This is just feed forward multi-layer perceptron. Yeah, 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 yeah. Okay, so to summarize the first part of this talk, I presented to you a way of developing architecture-aware perturbation bounds. They're based on exploiting the majorize-minimize framework, which of course is not the only way to design optimizers, but it is a fairly general way. But if you have an optimization technique that doesn't fit neatly into the majorize-minimize framework, these ideas may not capture everything you care about. And then we develop these architecture-aware perturbation bounds that can allow you to analyze how perturbation analysis can adapt as we change the width and depth of the network. And one thing that Jeremy likes to do when he thinks about this, because he comes from he did his undergrad in physics, is he thinks about having this fundamental yet practical theory of deep learning optimization. When we think about classic circuit design, we have these rules for building resistors. These are things you learn in first year EE class. So what is this theory of composite functions? What is this fundamental theory of reasoning about perturbations in composite functions that can potentially include more than just the learning rate? And so this is sort of a key sort of North Star that motivates a lot of this work. If you're interested in sort of more details, I highly recommend that you read the PhD thesis of Jeremy. It's actually very short. And so it's self-contained, built from first principles from the ground up, quite short. Jeremy is now, since graduated, now a postdoc at MIT, and he's really been the leader of this line of research. Any quick questions before I go to the second half of this talk? Yes?
I noticed that the optimal measure seems to be dependent on the number of epochs.
Yes.
Is that right?
Yes, yes.
Do you have any?
It depends on the number of, no, it does not depend on the number of epochs.
If you go to the plot, like scaling width and depth. Yeah. Is that right?
Yeah, so of course, this is an upper bound. This is an upper bound. The argument is that this is a more accurate upper bound than an isotropic quadratic. Yeah, it is an upper bound. Yeah. So with the optimality implied by this will never. I mean, like any upper bounds, it's not going to give you the exact right answer when you apply it in practice. But the argument is that it's a more nuanced and accurate upper bound of the majorization. If you really, really care about getting the optimal, yes. But in practice, if I gave you this green line in one run for a large network, most people would be satisfied. Yes?
When I saw the initial updates, it reminded me a little bit of algorithms like proximal gradient descent and Bregman,
Yep.
mirror descent,
Yep.
stuff like that. In particular, proximal.
Yep.
Would you be able to elaborate on the connection to these other?
You're talking about this one, right? Or
I'm talking about on earlier slides. Yeah, very, very early in the talk.
well, okay, and yeah, it's a special case of majorize-minimize. It's a special case of majorize-minimize. Yeah, they're all.
Proximal is?
Yes, I believe so. I mean, I don't want to be quoted on this because I haven't done the derivation, but I believe so. It's really just how you derive the majorization, which is the majorization architecture aware, yes or no? Yeah, that's the higher order bit.
I mean, it's different in the analysis. There's a lot
Okay.
of analysis technologies with proximal.
That's true.
You get the rate associated with the first term, you can also.
That's true. one could imagine merging the two. Yeah. Yeah. So if there are no further questions, let me present a little bit shorter, the second half of this talk. Which is on controlling the dynamics of the hidden layers. So that's the second idea we want to think about, how to control the sequence of activations of the hidden layers to somehow quickly and robustly converge to low loss, at least in some interesting applications. And as a warm-up, we're going to present deep neural networks in a different way because it's easier to transition into the mathematical formalism. So here, I'm going to present it in a way that kind of looks more like a dynamical system. Where you have the input, and then you have these hidden states, and the hidden functions, and the output. And then from this diagram, I want to then focus on ResNets. And what is a ResNet? A ResNet is sort of an extension or a modification of that earlier diagram, where you take the hidden layer activations of the previous layer, and you push it through, and then the hidden layer functions at each layer only adds a residual term, an additive residual term, to form the next layer. So that's what this formula here shows you down here. Okay. So the interpretation, as I'm sure many of you already know, is that you can sort of think of this as like an Euler integration of like a dynamical system, of a differential equation. And as you take the step size of this thing to 0, you get each of these functions f is kind of like the derivative or the dynamics of the hidden layer activations if you have like a continuum of hidden layers. And of course, that limit brings us to function classes like neural ODEs, where you have your input layer, which I'm not really going to focus on in this talk, but you have this continuum of hidden layers like this, which are these dynamics, and it's parameterized by a neural network. And then you have your output layer. Without loss of generality, let's say t is between 0 and 1 here. And a few comments. The forward pass to inference in these cases requires running an ODE solve. You can evaluate the output. Kind of interesting. You can evaluate the output at any time because of the requirement that these hidden layers have sort of the same semantic meaning throughout. And this includes this and generalizations of this includes things like continuous normalizing flows and certain types of generative models, amongst other applications that one could use these for. And the idea is that, okay, one can, once you think of this as a dynamical system, we can start to think about how one might use control theory to shape the learning of these dynamical systems. Control theory is commonly used to shape ODEs. What kind of properties do we want to shape these ODEs to obey? There are properties like stability. You don't want the ODE to destabilize for any trajectory, any inference trajectory in the ODE space. Safety. You don't want this trajectory to ever leave some predefined safe set. Adversarial robustness. If you have the first two properties under certain assumptions, you can get the third one as well. Like adversarial, like you're stable under adversarial perturbations. So why might you want to shape the dynamics of neural ODE? So this is work led by my student Ivan Jimenez Rodriguez. So here's just a simple toy example where we have a two-dimensional state space. So the hidden layer space is two-dimensional. And the color coding indicates at the end of inference what is the output class, blue or red. So let's say in this case the red class is correct for this particular input. And the purple lines, the quiver lines, are the dynamics of the ODE. So and this particular neural ODE was trained using standard backprop, the adjoint method, like in the original neural ODE paper. And then the black dotted lines are different trajectories under small perturbations of the input, which changes the initial condition, the initial point of the ODE. And it's unstable, right? You perturb the input a little bit, you get an initial condition of the trajectory that takes you to the wrong class. If you train the dynamics of this neural ODE to be stable, then they all kind of robustly and quickly converge to the correct class. And that's the approach that I'll be describing in the next 10 minutes or so. And we call it Lyapunov loss. So what dynamics can we shape? The first thing one might consider is to shape the full state space of the dynamics. So the full dimensionality of the hidden state. In practice, that can be too unwieldy, depending on the application. So what we instead do is we shape a projection of the hidden states. And one projection that immediately arises is the projection of the training loss. It is to just simply define the projection as the training loss, although there are other choices as well. But for presentation purposes, let's use this one. In other words, we want to analyze the dynamics of the training loss as we do this ODE integration. And in control-theoretic terms, you could think of this as a one-dimensional projection of the state space, just like any potential function. And the property that we're going to care about, although there are others one could care about, is called exponential stability. So this is just a quick one-slide sort of intro to exponential stability in the context of control theory. So exponential stability basically says that as I evolve my ODE in time, where time is indexed by little t, I want this potential function to decrease exponentially quickly with respect to the initial potential value. If we set the potential function to be the training loss, that means I want my training loss to decrease exponentially quickly as I integrate forward in time. The choice of the exponential is that it has this key invariant that's time independent, which is that at any point in time, the rate of decay of my potential function with respect to the dynamics of my ODE is a constant factor of my current potential. This is just a standard property of self-similarity between an exponential function and its derivative. This is just a standard implication. Yes?
How do you know what your training loss should be for the inlet?
So one interesting thing about neural ODEs is that you can actually evaluate the output at any time. You can do this for ResNet too, actually, if you really wanted to. Yeah. You could just apply the output layer to an intermediate hidden layer activation. You could also do this for ResNets if you really wanted to. Yeah. So that's the implementation detail of how you actually evaluate this. Okay, so this is just a pretty standard property people use in control theory. If you can show that the ODE dynamics satisfy this property within the state space that you care about, you get fast convergence and adversarial robustness under certain types of adversarial robustness. And so here's an example of adversarial exponential convergence in action. So the x-axis is inference time, 0 to 1. The y-axis is cross-entropy loss for a CFAR10. So we're just doing this for image classification just to showcase the presentation. And then the normal neural ODE trained using backprop is in red, and then our approach is LeoNet trained using Lyapunov loss, which I'll describe in a moment, is in blue. And it's just a demonstration of exponential convergence in practice. So the way we think about building up to Lyapunov loss and the training objective is to measure progress via this contraction condition that I just described earlier. So what I'm showing you here, again, is a two-dimensional hidden state space. The red and blue arrows are the dynamics of the neural ODE, and let's just say, for simplicity, that H star is the location in the state space that minimizes my potential, which is the training loss. And the parts in red are where the dynamics don't satisfy this contraction condition, and the parts in blue are where you do satisfy this contraction condition. Intuitively, if the entire state space was blue, we would satisfy this contraction condition everywhere, and we would have proven exponential stability of this ODE with respect to the training loss. So how do we get every part of the state space to be blue? And that brings us to Lyapunov loss. So first I'm going to define the pointwise Lyapunov loss, which is basically almost like a hinge loss, if you're familiar with hinge loss. So it basically says, if this condition is if this per state, if local contraction condition is violated, then that means this part is positive, then I pay a penalty proportional to the violation. If it's not violated, which means this part is negative, I just treat it as 0, I don't care. Yeah. And then the overall Lyapunov loss is the integral of this, over everything you care about. And achieving 0 Lyapunov loss almost everywhere, therefore implies exponential stability. So that's the LeoNet framework. You interpret any kind of training loss as a potential function. You instantiate this pointwise Lyapunov loss, and then you optimize this pointwise Lyapunov loss everywhere. That's sort of the high-level idea. A few quick optimization considerations. Of course, evaluating this integral exactly is hard. And so we do the simplest thing you can do, which is approximate by Monte Carlo sampling. That means we sample a data point, a training example, and a state uniformly at random or under some distribution. And then if it violates the Lyapunov loss, it induces a gradient. If it doesn't violate the Lyapunov loss, it has zero gradient. And of course, we do this in a batch at a time because PyTorch uses these batch gradient descents. Benefits of there are many benefits of doing sampling. It avoids an expensive ODE solve, so you don't have to use the adjoint method. And the goal is to minimize Lyapunov loss everywhere. So even if achieving Lyapunov loss under uniform measure, zero Lyapunov loss under your uniform measure, it also implies achieving zero Lyapunov loss under the original measure. And of course, similar ideas have already been used in other types of dynamical system-based machine learning approaches, such as score-based generative models, where you do this Monte Carlo sampling and then you use score matching. The key difference intuitively between score matching and what we're doing is that in score matching, you have an equality constraint that you're trying to constrain the dynamical system to satisfy. Whereas in this approach, we have an inequality constraint that we're trying to constrain the dynamical system to satisfy. But otherwise, this optimization procedure is kind of morally the same as what you do for score-based generative models. One slide, description on the connection to control theory. If you're not an expert in control theory, you can just sort of space out for 30 seconds. But for those of you who are an expert in control theory, a potential function V is an exponentially stabilizing control-Lyapunov function for a controllable ODE. If for all states that we care about, this property is satisfied. And this property, of course, is equivalent to Lyapunov loss for some theta. And in control theory, we think of theta as the controller. It's the control authority of the system, like the propeller blades of a drone or something like that. And so, we can sort of take this interpretation and ask the question, well, can we find a controller theta that makes this potential function an exponentially stabilizing control-Lyapunov function? Now, in control, normally, in what we model in control, F has uncontrollable dynamics, like gravity or whatever, and theta is relatively low-dimensional. In contrast, for these neuro-ODEs, there are no uncontrolled dynamics. Everything is controllable. Theta is very high-dimensional. So in other words, we can interpret neuro-ODEs as a super high-capacity controller, and we're just trying to find a control law, which is a parameterization of the neuro-ODE, that turns whatever objective function we care about into one that has control-theoretic properties, such as exponential stability. A few comments and extensions. You can stabilize the sets rather than points. Actually, stabilizing sets is more valuable in practice. You can do combinations of these conditions, like you do conjunctions of multiple of these conditions, which is useful for building up in real applications. And there are other invariances that you can care about rather than contraction. You can do forward invariance, which is implemented using what's known as a control barrier function rather than control Lyapunov function. But let me just tell you about the motivating application, why we even studied all this in the first place. And the motivating application is in continuous control, where we want to model the controller using a neuro-ODE. And then we want this controller to make sure that the robot, in this case, a biped, its state space never leaves an unsafe set. So for example, its torsal angle never leaves a certain set, and the swing foot, as it's walking, never leaves a certain set in the state space. It's known from domain knowledge that if you can guarantee these things, then it implies indefinite walking forever into the future under sort of a bounded set of perturbations. And so you sample states in the state space. It's an ODE. You have a controller as part of this. You have a neuro-ODE controller as part of this. You compile your Lyapunov loss. Actually, in this case, it's a barrier loss, but it's mathematically the same form. You deploy the controller, and then you do this process. And that leads us to the neuro-gates approach, which, to the best of my knowledge, is the first neuro-ODE-based controller for bipedal locomotion with forward invariance guarantees. And so if you're interested, you can check out the paper. A quick aside, we can simply doing Monte Carlo sampling won't actually give you the guarantee, because Monte Carlo sampling is something that happens in expectation. To actually get the guarantee, you of course you have to do a little bit more work that's related to formal verification and certifying that you actually have zero loss or at most epsilon loss everywhere. I won't go into the details of that, but if you're interested, you can check out this paper. Okay. Yeah, sure, go ahead.
So from my experiences from applications of older days, often had the problem that when I worked at Microsoft, we were interested in the formal verification for certain things. But it always
Yes. So this is also slow. So first, a few comments. I'm not sure what the dimensionality of the space you're verifying, but this robot, this robot, with enough domain knowledge, because there's this way of characterizing bipedal locomotion using what's called zero moment point dynamics, and basically what the TLDR is that you can compile everything down to a low dimensional state space that's at most 6-dimensional. So one of the key things, it's still hard, of course, but when this approach that we developed, we've scaled it up to about, don't quote me on this, but about 16 to 32 dimensions, which is useful for a lot of real robots, of course not universally applicable. And of course it's also specific to things like neuro ODEs.
So the 16 dimension can deal with the form of that.
Yes, we can. We have certified for, we can certify, yes. This particular robot is, the degrees of freedom is like 4 or 6. Yeah. Yes, question?
So going back to, I think, the first figure you showed the spectral, like, across the top, I'm wondering, can you, like, with this design, can you control where the equilibrium lies?
So can I synthesize an arbitrary potential function?
Yeah, because, like,
Yes.
maybe the fault that you showed.
Yes. So I should have spent a little bit more time talking about related work. So there are people that try to synthesize or search for a V given a dynamical system, and then there are people who, what we do is given a desired V, because we have a high capacity over-parameterized controller, a neural net, just find the parameterization. What you're describing probably will require sort of both sides to sort of be applied in a unified framework. Yes?
I guess my question is, I'm wondering how your method affects the overall or converted performance of the model that you're training. When you're imposing, like, at each hidden layer, that each layer sort of like exponentially decrease some loss function that you're imposing. Going back, when you train with ResNet, each layer learns to sort of pick out certain features of the image, and then that helps it perform or give some sort of accurate prediction. It seems like in your method, you're sort of imposing what might be learned at each hidden layer. So I'm wondering
That is a really, really, really great point. So it actually strikes to a limitation of this framework, which is a lot of this is based on an engineer with a spec that they really care about and imposing that spec on the behavior of this neural net. And if your spec is over-specified, then you actually you overly constrain your neural net and you reduce performance. And so that actually speaks to a more deeper philosophical question, which is how do I do this to get the best of both worlds? And I wish I can give you an answer for that, but maybe you'll tell me how you did it next year.
I think relevant to that point is, so you're kind of assuming that your objective loss is like a valid Lyapunov function, like it's a valid globally.
You're assuming that there exists a parameterization of the neural network that turns this into a Lyapunov function.
And then, like, if those assumptions break down, maybe like the.
Yes, it's related to, correct. It's related, so in control theory, there's this idea of controllability. Like, is this system controllable? And the analogy to what you're saying is this system learnable? Right? In learning theory, you have to say, oh, is this problem even learnable? Does it even exist a solution? And it turns out, at least for this specific type of problem, learning theoretic problem, or learning problem, the controllability of the dynamic system is directly analogous to the learning ability of the underlying analogous learning problem. Yeah. So we're assuming that there exists some theta that can achieve zero Lyapunov loss everywhere. If that's not true, then this whole thing doesn't work, but we're living in the over-parameterized regime, so we just assume it's true. Okay, so just to summarize, I present you in the second half, control-theoretic shaping of neuro ODEs leads to this Lyapunov loss applied to bipedal locomotion. And maybe just to take one step back, and I'll conclude, I hope I've convinced you that there's interesting progress that can be made in building a structure-aware theory of deep learning. Neural networks are not arbitrary black boxes, and analyzing its structure can lead to more nuanced theory and unlock new connections, such as per-layer perturbation analysis and contraction analysis. And if you're interested in any of the papers, they're available here. Thank you for your attention.
Thanks. If there are questions, raise your hand. I'll bring the mic around. Maybe just to kick it off, there wasn't much talk about stochastic gradient descent.
Correct.
Or stochastic methods in general.
Yes.
In the talk, which is a little surprising. And also, when I think of neural nets, why are they different in the optimization world than classical optimization? It's stochastic methods and it's automatic differentiation. Neither of those really came up in the talk. I wonder
Perfect.
what you could say about both of those.
Great. So I guess on the topic of stochastic gradient descent, I guess it depends on which angle you're going for. There's one angle which is maybe a bit too oversimplified, which is something like we do stochastic gradient descent in part because it leads to just faster optimization. Per iterate, batch gradient descent is faster per iterate, but it's just computationally much slower. So from that perspective, if we develop this theory first for batch gradient descent, and then we just full batch gradient descent, and then we just approximate the gradient with mini batches, which is an approximation because our theory doesn't handle it. But then when we start there, we can build it from this perspective. If there's a different perspective you're coming after, which is some form of like regularization, then it's a little bit more complicated.
No, I want the first point. I mean,
Okay.
it's way faster.
It is way faster.
And
yeah.
there's no reason you can't start to merge these ideas, but it's not going to be trivial because step size choice is a very different beast. than
Correct.
stochastic
And
model.
that is actually a great direction for future work when we didn't start there. No.
Great.
Yeah.
What about automatic differentiation? I mean, a lot of your terms.
All of these
they
terms
kind
are
of
compatible. All of
calculated
these
automatically.
Yeah, all these terms are compatible with automatic differentiation. Yeah. You can stick this into Mosaic Composer if you wanted to. Yeah.
Anybody else? Yeah.
Thank you, Mike. I have a question also related to this websites. So the principle you used to set up this website is still based on a greedy principle. You want to maximize the outcome of one gradient step.
Yes, it's based on the majorize-minimize framework. Yes.
That's right. So, so how much do you believe this is like a right way, the right way to go?
I see. So how much do I believe in majorize-minimize writ large, just in general?
Because like if you really tune the step set, you should very much like you shouldn't be greedy for one step, right? You should be more aggressive than that.
You mean like Nesterov?
I don't know, maybe.
Okay. Honestly, it's a great question. Honestly, I haven't thought that much about it. Because it just never, I have never seriously entertained something that's not based off majorize-minimize. Maybe that answers your question. But no, it's a good question. I just never really considered it. I think part of the reason we never considered it is because there's so much work left to be done in this framework, as mentioned earlier, with deriving the right step size with gradient, stochastic gradient descent is already like a non-trivial step. So I haven't gotten to the point of reflection on this research direction where I've actually thought about that question. Yeah.
Thanks.
There's time for maybe one more question. Anybody want to? All right, well then let's thank Yisong. Thank you for the talk.